You're here because you want to master chemical bonding with a University of Cambridge graduate. Let's begin. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. Before we begin, be sure to go into the link below so that you can download a free copy of my notes and use it to follow through our lesson today. We have to understand the different structures and bonding of our different kinds of compounds or elements in order to better appreciate or predict what chemical properties and physical properties that each of them can undergo. So for structure and bonding, it is actually very simple. All you have to do is you have to follow this answering technique where the molecule or compound or atom, right, exists as a what structure with what main bonding or force, and this is between what molecules or atoms or ions, so be specific, and then you proceed to explain using this structure and bonding, right, how this relates to the physical or chemical property in question. If you use this structure, you can never go wrong. I repeat, you can never go wrong, right, for chemical bonding questions. I see too many students who try so many different kinds of answering techniques. It's like the schools aren't teaching them properly. So just follow this structure and you just can't go wrong. Now what's missing is knowing how to identify the different structures, and also for each structure, what is the main bonding or the main force. So first up, if there is covalent bonding, okay, in your molecule or in your compound, right? The first thing you should think about is that it's probably a simple molecular structure. So for example, your water, which is H2O, your chlorine, or even your oxygen molecule that we went through just now. These all exist as simple molecular structures that have intermolecular forces of attraction between the molecules. For the properties, they tend to have low melting point and boiling points. Why? This is where you explain in relation to the structure and bonding. This is because little energy is required to overcome the weak intermolecular forces of attraction. It's also a non-conductor of electricity in any state. Okay, and the reason for this is because your electrons, right, are actually localized in covalent bonds, or they are localized in electron shells. So therefore, these electrons are actually not mobile to conduct electricity, and thus there is actually a lack of mobile charge carriers. So what's the sample question for chemical bonding, and how can we use our newfound chemical bonding answering technique to answer these kinds of questions? Here's a look at an example. Let's say a question asks you, explain why O2 has a low boiling point. First, you need to know that O2 generally is a non-metal and a non-metal, so there's covalent bonding between them. And we need to know that it is a simple molecular structure. So here we answer that O2 exists as a simple molecular structure with weak intermolecular forces of attraction between the O2 molecules. Realize how I'm being specific about what kind of molecules is between. Then you explain in relation to the property. So here we say little energy is required to overcome the weak intermolecular forces of attraction, and thus it has a low boiling point. End it off with a concluding statement. Realize that all you had to do was just memorize the structure and memorize the force and memorize how to answer for the specific physical property, in this case, low boiling point. And you can easily get your full marks. Now, another kind of structure that is also important for covalent compounds is your giant molecular structure, where the main bonding is actually the covalent bonds between the atoms. For this, even though there is covalent bonding, there's only a few examples you need to memorize that actually have this giant molecular structure. So again, I say, if it has covalent bonding, it generally is a simple molecular structure, unless it's one of these examples: diamond, graphite, silicon, or silicon dioxide, or any other thing that they give in the question that has the same structure as I have drawn up. These are all your giant molecular structures. Anything else is out of syllabus and you don't need to know about it. So to understand the different physical properties of your different giant molecular structures, you need to know that it really depends on the structure itself. For example, let's say you have a structure like diamond, right? There is typically this structure over here. You just need to recognize this pattern, right? They tend to have a high melting point and boiling point. Okay, so they have a large amount of energy that is required to break these strong covalent bonds between the atoms. It's also a non-conductor of electricity in any state, again because the electrons are localized in the covalent bonds and are not mobile to conduct electricity. It's also very insoluble in polar and non-polar solvents. Again, think about your normal diamond. Okay, if diamond was so easily soluble, it wouldn't be so precious, right? This is because of the strong covalent bonds. They are too strong, right? So to break, no interaction can actually compensate for the energy required to break this bond. Okay, so that's why it's very insoluble in a lot of solvents. Okay, next, right? It is very hard and strong and non-malleable. Again, it's very strong characteristics because of the strong covalent bonds. However, we actually have a different giant molecular structure, right? Which is graphite. Graphite is also carbon, by the way. And this special structure is just layers of atoms that are held together by the strong covalent bonds. Okay, as you can see, each line over here, okay, is representative of a covalent bond, and each dot is like a carbon. Okay, it's a carbon, 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 carbon. Right? So first it forms these layers of carbons that are covalently bonded in a hexagonal arrangement. And then you see these dotted lines over here. So actually between these layers, right, there's a force that is between these layers that's holding them together. These are called the intermolecular forces of attraction. So to explain this structure, you have to be very specific in saying that each atom is bonded to 3 other carbon atoms, right, by strong covalent bonds. And this creates layers of your carbon atoms. Now, each carbon atom usually has 4 valence electrons. But since they only went through 3 covalent bonds, that means each carbon atom actually has 1 more electron left. And this extra electron is actually delocalized. Take note of this keyword over here. Okay, and I've already mentioned about the intermolecular forces between the layers of carbon atoms. So, when you're explaining the physical properties of graphite, let's talk about this structure specifically first. Then, we can explain in correlation to the structure. So, why is graphite so special? Okay, unlike diamond, it's a conductor of electricity. Okay, and this is because, as I said just now, each carbon has a delocalized electron that can act as a mobile charge carrier. Okay, it's also very soft and slippery. This is because there are weak intermolecular forces of attraction between the layers of carbon atoms, as I've also said previously. Now, what's the significance of this? This is because, right, the layers can actually slide over one another easily with these weak intermolecular forces. It's easy sliding because the intermolecular forces are so weak. Not a lot of energy is required to overcome these intermolecular forces of attraction. Now let's talk about ionic bonding. Okay, as I've said just now, ionic bonding is between a metal and a non-metal, right? The structure of your ionic bonds is called a giant ionic lattice. The main force is the strong electrostatic forces of attraction between the oppositely charged ion. And you would do best to name the specific ions when you're answering your question. So let's take a look at this diagram over here. We know, for example, sodium chloride is an ionic bonded compound, right? And while it does look like this, right, in actual fact, the actual structure will look something like this. And this is a small representation of the lattice structure where the ions, right, are alternating, right? And because they're oppositely charged, right? Okay, it's not like 1:1. Technically, this sodium is kind of like bonded like 3-way, like this. Okay, and this is pretty cool, right? And this is just a small fragment. So you can imagine a whole column and a whole row, a whole cube, okay, of all the ions that are alternating. Okay, and these strong electrostatic forces of attraction between the opposite charges, Okay, this is what is holding them together. So what are some of my factors that can affect the strength of my ionic bond or the strength of the electrostatic forces of attraction? Well, you want to look at the lattice energy, right? So you don't need to know this specifically, but lattice energy is determined by this formula over here, right? And as you can see from this formula says that the lattice energy is proportional to the charges of the ion multiplied together divided by the radius of the ions. Okay, this is called ionic radii. And you can see from this formula that actually charge has a more significant impact on lattice energy than ionic radius, but both still affect the strength of your ionic bond. So what are some of my properties of ionic bonds? Well, they tend to have high melting point and boiling point because, again, there's a large amount of energy that's required to overcome the strong electrostatic forces of attraction between the oppositely charged ions. It's also very strong and hard, again due to the electrostatic forces of attraction. However, one unique thing about ionic bonded compounds is that they are very brittle. This is because the lattice structure usually alternates between the oppositely charged ions. If you put a force, to make the layers of ions slide, it will lead to repulsion. This repulsion, as shown by the diagram over here, will lead to massive repulsion and it will break apart the whole ionic lattice. Hence, it is very brittle. It is also a non-conductor of electricity in the solid state because the ions are in fixed positions in the lattice structure. Remember, they're held together by strong electrostatic forces of attraction. So because of this, there is no mobile charge carrier, so it cannot conduct electricity. However, your ionic compounds are conductors of electricity in the molten or aqueous state. It's because in these states, right, your ions are more mobile, and they can actually act as mobile charge carriers. Next, your ionic compounds are also known to be soluble in polar solvents. This is because they form very favorable keyword ion dipole interactions that are between the ions and the water molecules. This interaction is actually strong enough to compensate for the breaking of the ionic bond. Now it's a new kind of bonding that we've never really talked about before. This is called metallic bonding. This usually happens for our pure metals. For example, sodium, just pure sodium or pure iron, right? And the structure of these is called a giant metallic lattice structure with strong electrostatic forces of attraction between the metal cation and the sea of delocalized electrons. And here's a little diagram which you must absolutely know how to draw. Where your cations are little blobs over here, right? And they have electrons that are delocalized. It seems as though the electron is kind of tagged to the ion, but the electrons are actually delocalized, so they're actually flowing, and they're not in one particular spot. Now you must know that the factor affecting the strength of my metallic bonding is the charge density. Your charge density is dependent on the charge of the ion, and the ionic radii. Again, this is what determines the strength of the metallic bond. Next, let's look at some of the properties of metals. Our metals, right, tend to have high melting point and boiling point because a lot of energy is required to overcome the strong electrostatic forces of attraction between the metal cations and the sea of delocalized electrons. As you can see, there's kind of a pattern here where things with electrostatic forces of attraction tend to have high melting point and boiling point. Next, they also are good conductors of electricity in the solid and liquid state because of the sea of delocalized electrons. These act as mobile charge carriers. Lastly, right, your metals tend to be malleable and ductile. This is because there is stress that can be applied to the layers of metal cations and it will cause them to slide easily, right? Because it's so easy to slide, right? That's why we say it's very malleable or ductile. Malleable means that you can easily bend it. So you can imagine like your copper wires, for example, right? You can easily bend them, right? So it's very malleable. So kind of related to metals, we have to talk about alloys. And please know the definition of alloys. Alloys are a mixture of metals and one or more elements. So for example, steel, right, typically contains iron, right? But this is melded together with carbon and small amounts of other elements. So why do we use alloys, right? Because it has some of these special properties. Number one, it is harder and stronger. Number two, it sometimes looks better in appearance. 3, it tends to have lower melting point. And 4, remember that it is very resistant to corrosion. So it's mainly because of this, and this, right? That's why we tend to use alloys. Now, the question is, why are alloys typically stronger and harder or less malleable than your pure metals? Okay, because when you mishmash other elements with the metal itself, these elements or these atoms, right, tend to have different sizes. Right, so when you form these alloys, right, these different elements are combined in the layer, but because they have different sizes, it's actually harder to slide the atoms. Okay, and because of that, your alloys tend to be stronger or less malleable because the atoms cannot slide. Now, lastly, right, sometimes you'll be asked, what is the difference between elements, compounds, and mixtures? Well, elements, okay, tend to contain only one type of atom, right, and they cannot be broken down into any simpler type of matter. So, for example, right, helium or oxygen. So do take note, just because there's more than one atom in the molecule, it still means it is an element, right? For example, oxygen, O2. Just because there's 2 oxygen atoms does not mean that it is not an element. It is still an element because it has only one type of element. Next, compounds, right? These contain atoms of 2 or more different elements bonded together, and this can be chemically broken down into its elements. For example, sodium fluoride, NaF, or CO2. As long as there's more than one different type of element, it is generally a compound. Next, we have mixtures, right? Mixtures, they generally contain 2 or more elements and or compounds that are mixed together. Remember, they're not bonded, right? They're just mixed together in the same pile, all right? And these can be physically separated into different components. For example, alloys, which we've already went through, are mixtures of metals with other elements, or your air. Air is a very common mixture that you can think about. Air has different molecules, right? For example, your carbon dioxide, your oxygen, your nitrogen gas, and many more. If you enjoyed today's video, do remember to click the subscribe button so that you can enjoy more free content from us and improve your chemistry with us together. If you want to join my community of students to learn more secret formulas to acing chemistry, do check us out in the link below and sign up for a free trial class today.